Okay, now let's do some examples concerning the Gauss-Jacobi and Gauss-Seidel method. And we will begin by just generating a new script. And so the name of my script is function MECH310 Gauss-Jacobi. So remember that Gauss-Jacobi and Gauss-Seidel are iterative methods for solving the linear set of equations. Again, I will put two commands, clear all and close all, in order to close all the windows that are opened by the Matlab and clear all the variables which are created by the Matlab. Now, next step is to define the size of the number of equations. So let's say that this is 10. I1 is equal to 1 to n Okay, so first let me generate the right hand side of the equation, bi1. I will just say that I1 for J1 is equal to 1 to n, and let's do it like this: I1 J1 I1 plus J1. So let's say that this is our matrix. First step is to calculate the determinant of A. So this is that A. Of course, B has to be a row vector, so I will take transpose of it for the use in forthcoming calculations. So let's check the determinant of A and let's see what the value is. I will evaluate it. Yes, save the script with MECH310. So the determinant is 0. Oops, that's very bad. Now let's do something else. That is minus 1 multiplied by J1, and this is multiplied by minus 1 to the power I1. Let's check the determinant of this matrix. It's a very small value. Let's check the condition number. So the determinant of the matrix is very small, but let's put a condition number of the, that was I, eigen values of A. Yes, now condition number of A, that is the maximum of absolute value of the eigenvalues of A, we will divide it by the minimum of the eigenvalues. I will just copy and paste. So this is the minimum. Let's check the condition number. Wow, 10 to the power 17. So it's a very big value. So let's say that this is +1. It will not change something significantly. Okay, still the condition number is very big. So remember that both Gauss-Jacobi and Gauss-Seidel methods are worked pretty well with the diagonal dominant problems. So let's create a diagonal dominant equation. So remember that the absolute value of the sum of the values of the off-diagonal terms has to be equal to or greater than, or smaller than the diagonal term. So this is, let's say J1 is equal to from 1 to I1 minus 1. Then let's say that there exists a sum value. Sum value is equal to sum value plus A I1 J1, but absolute of it, I will take the absolute value of it. Okay, this means that the sum value has to be 0 here. I will just copy these lines and paste it here. Now this has to be I plus 1 to n. And let's check the condition number. Well, okay, so we forgot something. This is I1 to I1 is equal to some value. Let's put semicolons here. Okay, so the determinant is very large, but the condition number is pretty well. It's 10. That's okay. So let's see how it works, or whether it will work or not. So the condition number is pretty good. Our matrix is diagonal dominant. Let's put a breakpoint here and see our matrix. I put the breakpoint on line 21. I run the code. It stops there. I double click on one of the A's and I see the matrix here. There is another way. I right click and I say that open A. Now I have the values. So as you see, the largest term is on the diagonal always. So we have a diagonal dominant matrix. Is it symmetric? So it's 9 here, it's 9 here. Yeah, the matrix is symmetric as well. We can generate a non-symmetric matrix, but let's leave it so at the moment. Okay, now let's check let's calculate the inverse of A. And we multiply the inverse of A with B matrix. This will give us the X inverse, let's say, X from inverse. Let's check the values. I forgot the breakpoint, so no problem about that. Okay, so I have some values here for the X values. They seems to be that they're at an order of 1. It's okay. Now let's check the error. X A multiplied by X inverse minus B is the error. Now I will calculate the L2 norm of the error. So what's an L2 norm? In fact, it is the square root of the squares. Because I need a scalar value for the error. And I cannot, so I need some measure for the error, in fact. So remember that how we calculate the magnitude of a vector in statics. So since we have a vector here, error is a vector, we want to calculate its magnitude. That's much more logical. And error is a column vector, therefore I take the transpose of it, then multiplication of the transpose with the with itself. This will give a scalar value. I say that it is L2 error. And I will take the square root of it. So the error is 10 to the power minus 14. It seems to be okay. So I will leave it so. Let's put a semicolon on these lines on line 28 for the X inverse. I don't need these values at the moment. I will use it for in the forthcoming operations. Now let's begin our Gauss-Jacobi iteration. First, I need an initial guess for the X values. I can choose any value. Of course, the starting point is always important. but for the moment I will choose it as 1. So I created loop in order to assign the values for the x. Remember that now x is a row vector, therefore I say that x is equal to transpose of x, and I make the x as column vector. Now I need an error bound. Error s, because I will continue to make an iteration and I will look for the solution iteratively. So this can be some value, let's say that 0.01. Now I have approximate error. Just I give a number which is larger than error s, because I will use while loop for the iteration. And then I define it. Okay, so let's say that while error a is greater than error s, do something. So this is my Gauss-Jacobi iteration. Now first thing is I will go from I1 from 1 to 10, because I will calculate the value from each iteration. And the second thing is, now I need the values from the previous iteration. This basically means that I have to assign a vector which has the values of x from previous iteration. Let's say that xp. Okay. Now, what I do is I sum up the values, contribution of the values from the previous iteration. So remember that I have unknowns and I get the values, I use the values of the previous iteration in order to calculate the pivot variable in the pivot equation. So what I do is very simple. I will generate another do loop. Let's say that this is J1. Now this J1 is equal to from 1 to I1 minus 1, because I have the current index and I use the values before than the current index. So as you see, this is the Jacobi iteration, and in fact here, for example, in order to calculate the second unknown, I sum up the values and well, sorry, it's not the correct slide. Okay, here is the correct slide. So we use the values from the previous iteration. So x2i, x3i, and x and I, and we multiply them with the corresponding coefficients, and then we subtract it from the right hand side of the equation, and then we divide the whole expression with the a11. We obtain x1 from here. So this is how we obtain the x1, and it is the same for the x2. As you see, we just exclude that variable from the equation and put it on the, leave it on the right hand side, left hand side alone, and then we sum up the rest and divide it with the pivot coefficient. Now at the moment we don't need to make a pivoting because we already created diagonal dominant matrix. So we will continue like this. Now let's return back to Matlab. So now I'm summing up the value. Sum value equal to 0. Now I will put the sum here. Sum value is equal to sum value plus a I1 J1 multiplied by x previous. So this was the value of the x from the previous iteration. In the first step, it is the initial guess. I will copy these lines, these 3 lines, because now I will sum up the values from the contribution of the values from the variables after the pivot variable. So this is I1 plus 1. So remember that our pivot is I1, and this is to the n. Now after summing up these values, I will subtract it from vi1 sum value. This is equal to x I1 then I will divide this expression with the pivot coefficient. Let's put semicolon here. I don't want to see them on my screen, and that's okay. So these are the x values. Now let's see how it works. Let me put a breakpoint here. Okay. So all of my x's are 1. Make the first iteration. Now the values are beginning to change. As you see, it's changing. Now let's check for the error. So I will look for the relative approximate error, x minus x previous divided by x multiplied by 100 error A I will put a continue line here. for the debugging purposes. So these are my errors. Well, it creates a matrix. So let's put a dot here. And let's check. Yes, now I have the vector. Okay. So now let's calculate the L2 of the error. Relative approximate error. So it is again, so the error is error A is a column vector. Therefore, I will take the transpose of it. A scalar multiplication of it with the error A, and then I will get the square root of it. Now what I'm going to do is I will say that this is L2 and this is L2. Okay, so I just changed the name of the variables in order to be consistent. Let me check my script. Okay, I will run it once more. Error A. So this is L2 and this is L2. Oh well, square root is not typed correctly. Okay, it is 587. It's going down, but it's highly oscillatory. Yeah? Okay, let's do something. Let's say that here is my iteration, and iteration is initially 0. And let's see how many iterations will it take. Iteration is equal to iteration plus 1. And I will add in another line here. So error vector is iteration, that is L2 error A. And let's plot it. Figure plot error vector. Okay. Now I got the results. But let me share the figure with you if I can see it on my screen. So there are lots of things and I don't see it, the figure. I have, okay, it's here. I hope you see it. So it takes about 70 iterations for the convergence, and L2 norm of the error goes up to 9,000%. Here it goes up like this, so it's not monotonic, it's highly oscillatory. Let's return back to Matlab and let's check it in a log plot. In a log. I think it was the log. Let's check it from the help. Yes, it was the log. I will run it again. Now I have the results. You will see it within a minute. Okay, so here is my error with iteration in a logarithmic plot, because this is better. Certainly the orders of magnitude can change significantly, and better is to observe the iteration versus error in a log plot. As you see, the error is at an order of 10 to the power 3 at the beginning. It goes up to 10 to the power 4. Then it is oscillatory. It makes very high oscillations, and then it begins to decrease like after 20 iterations in a monotonic way. But before then, it was non-monotonic. Okay, so this is the Jacobi iteration. Fine. Now let's keep it and return back to the Matlab. So now next thing is to play with the line of the error vector. Okay. So title is the error. And the Y level is the L2 error. Oh, now we have a better vision. Better, the figure will be seen better. This is how it works. As you see in a log-log plot, we have the red line going up and down, and then decreases monotonically. Fine. So it takes about 70 iterations. Now we have seen something. Remember that we have an under relaxation, and see the effect of under relaxation. Now let's say that x is equal to alpha multiplied by x plus 1 minus, sorry, it was lambda in the slide, so lambda. 1 minus lambda multiplied by the previous iteration. So this is basically how much of the alpha we are going to get, lambda we are going to get. So this is a linear interpolation. So let's choose lambda. And let's see the effect of so we know that when lambda is equal to 0, it will stay at the previous iteration, and I can choose lambda between the beginning from 0 to some value. Choosing very small lambda means that you will progress with very small steps. But let's see how the things will change. Now I choose 0.1, and now let's see what is the effect of 0.1 on this matrix. So first, the error was almost constant. Sorry, you don't see it. Let me share the figure and make it visible for you. Okay. So at first, so you see that it's almost constant, and then there is a peak. It goes to 10 to the power 5, very sharp rise, and then it decreases, and then it begins to decrease almost monotonically. So, and it takes about 1, 2, 3, 4, 400, 500 iterations now. So 0.1, choosing 0.1 increases the iterations, but the error decreases almost monotonically. Let's play. Now I will close the screen. I will return back to the Matlab, and it will begin to increase in a step-by-step manner. Or let's do something else. No, let's do it in a step-by-step. 0.1, and then I will continue with the 0.2. Now let me share the screen for the error. You see that now there is no sharp rise. So remember that without the under relaxation, now we are doing under relaxation simply because alpha is between 0 and 1. So you see that it begins at an order of 1000. So it's 587. And then it goes 1700. So remember that without the under relaxation, it was almost 10,000. So at an order of 10 to the power 4. But now the value is at an order of 10 to the power 3. And as you see, the number of iterations was 400. Now it's at an order of 300. And again, it's monotonically decreasing. There is no oscillations. Now these oscillations, I will tell you something about these oscillations, because these oscillations in the error is sometimes gives a clue to you how how you approach to the solution. Okay, let's return back to the Matlab again. I will increase one with steps of 0.1. So it is 0.3. You see, now again, the peak value begins to increase and goes up to 10 to the power 4, but still it decreases monotonically after that. So it is just after the second iteration. So we can say that the decrease is monotonic and the number of iterations is at around 200 now. So the number of iterations begin to decrease, but the convergence is monotonic. Now let's make it 0.4. We are just trying to find the optimum value for the lambda. So as you see now, the peak value is 1000, and the convergence is again monotonic in a log plot. So as you see, the total number of iterations is 130. Okay. So now let's increase by steps with the steps of 0.2. Now it was 0.4. Now let's say that 0.6. Okay, now this is what is desired. You see, it is completely monotonic. It decreases completely in a monotonic fashion. So the error is less than 10% after 7-8 iterations, and around, and then begin to decrease again and goes to 0, and there is no sharp rise. Let's check where the value for the 0.8. Now, as you see, again, um, there are some oscillations in the error in the convergence history of the technique. Now, this basically means that we are around the optimal value for the under relaxation coefficient is around 0.6 for this problem. And in many cases, it is almost impossible to predict it. So you just find it by using the trial and error. Once you fix it for a certain type of a problem, then you will continue with it. Okay, so this is the story with the under relaxation. We know what the case is for one. But how about the over relaxation, successive over relaxation? So I will put lambda as 1.2. So remember that we had 70 iterations. Now this is the over relaxation history. You see that the error goes up to 5,000 and then it decreases monotonically. And then the error is very high, it's 700% for this matrix. Even the matrix is well conditioned, it's diagonal dominant. Over relaxation seems to not help. But let's see, let's continue to increase with small steps. Let's make it 1.4. Maybe we are still far away from the optimum. Okay, so again, the peak error is 10 to the power 5. And at a certain value, you see that it is 700%. Even you exceed the value of 1,000. So now it was 1.4. Let's say that it's 1.6. Again, it goes to 4,000. Now we have more monotonic. The error is constant for a large set of equations, but suddenly it decreases below a value. So we can say that this result, even though it seems to the error is below a certain value, this result is not reliable. But let's continue. So it is 1.6, 1.8. Now new share. I will share the error with you. Okay, so now as you see, again, it goes up to 10 to the power 4 and then it's almost constant. So it is around 700, the error is 700%. And the total number of iterations is approximately 1000. Suddenly it decreases below a certain value and the machine thinks that it's converged, but actually this solution is not converged still. We will have two more trials with this. I just want to put two. Normally the book gives that it is the upper bound is 2, but normally it can be any value for over relaxation, which is greater than 1. So now, as you see here, now the number of iterations decreases. So it is again 700% and 800 iterations. So it is constant for a large number of iterations. Error does not change. Let's see what happens when we put 3. So this is what happens when the lambda is 3. This is the graph. Let's say that 10 or 5 maybe. That will be my last trial. I will say 5 for the under relaxation, over relaxation, or relaxation coefficient. So this is the result for 5. So basically the error grows and we cannot say that for this matrix, for example, over relaxation is the right choice. Okay, so this is the thing related with the over relaxation and under relaxation. Now, the point is, what if we use Gauss-Seidel? I will modify. So Gauss-Seidel is basically the enhanced version of the Gauss-Jacobi method. I will say save as, and instead of Gauss-Jacobi, I will change the name to Seidel. Now let's go back to the slides and let's see how the Gauss-Seidel method works. So this was Gauss-Jacobi. Now in Gauss-Seidel method, you got the values associated with the this has to be I plus 1, by the way. Just correct it. And this is also I plus 1. So you get the values from the current iteration. Okay. So in Gauss-Seidel method, basically what you do is very simple and straightforward. For the first iteration of for the first equation, for the first pivot equation, certainly you use the values from the previous iteration in order to calculate the new value for the pivot variable. But for the next one, you also use, now you have an updated value. And you use this better approximation. So you use xi plus 1, value from the xi plus 1, and it goes like this. Since you have the updated values, you can use these updated values in the forthcoming equations. This is how the Gauss, this is Gauss-Jacobi. Gauss-Seidel method works. Just a moment, maybe I have. Yeah. This is how the Gauss-Seidel method works. Now, let's return back to our Matlab script. And just, we have the same matrix. I will begin with the same initial value. Everything will be the same. Just I will choose lambda as 1. So I will not use any relaxation. And now I have the x previous, right? But in fact, in my new matrix, I don't need the x previous. I only need the value from the x, because the x values are completely constantly updated. So this is what I'm going to modify. Now I don't need the x previous. This will decrease the memory, allocated memory, amount of allocated memory, and I don't need the x previous for the computation. I will just use it for the under relaxation. Or over relaxation, to show the under relaxation and over relaxation, and for the calculation of the error. Now, I have the Gauss-Seidel, and the rest is all the same. Let me check once more. Yes. Let's run it. Now I got the results for the Gauss-Seidel. Let me share the error distribution with you. Okay, as you see, error in the first iteration is almost constant, and even though I didn't use under relaxation or over relaxation, it converts at 12th iteration. So remember that when I didn't use any relaxation, it was 70 iterations. And the error was not monotonically decreasing. Now I have a monotonically decreasing error in Gauss-Seidel method. because I constantly update and I have a better approximation for the for some values. So this is how the error decreases in Gauss-Seidel. Now, next thing is to see the effect of under relaxation. Let's go back to Matlab and change the lambda. .1, and I will run it. Now remember that it was 12 iterations and the error was monotonic, and taking 0.1, again the convergence is really monotonic because the matrices were conditioned, no problem about that. But now it take about 200 iterations in order to in order for the method to convert to the solution. So this is what the case is. Now let's use, remember that it was 0.6 for the Jacobi iteration for this matrix. I will use 0.4, for example. Let's see the value convergence history for the so again, it is monotonically decreasing. So it is stuck somewhere here in after the 10th iteration, and the error is 40%, and then it continues to decrease monotonically. Okay, so this is one thing. Let's return back and let's check 0.6. So remember that 0.6 was the optimal under relaxation coefficient for the Gauss-Jacobi method. Again, it converts about 15 iterations here, as you see. Sorry, 55 iterations. And the error is again monotonically decreasing. Okay. So we know what the value for the one is, and let's check how about the over relaxation. And let's try 1.2. It's okay. So it seems to be that we have converged result in 12 iterations now. Sorry, in 25 iterations. Yes, it's 10, 20, 25 iterations. So it was before 50 iterations. That's my mistake. So let's change the type of the plot. Maybe that's better. Instead of log-log plot, let's change it to log linear plot. need to find the command for the log linear plot. Okay, so it is semi-log y in MATLAB. Okay, so this is the semi-log y plot. So we have logarithmic scale on y-axis and we have the linear scale on the x-axis. And we see that it takes about 25 iterations for 1.2 for the over relaxation. And let's play with the over relaxation coefficient. So it was 1.4. Let's say that it's 1.6. So this is the convergence. It takes about 30, 35 iterations. And as you see, the error begins to be non-monotonic. Let's say that, let's exaggerate and let's say that it is 5. I'm just curious about the result. And the result is completely disastrous when it's 5. Let's go back. So it was 1.6. Let's say that it is 1.4. It is not that optimal. So let me share it with you. So this is the convergence history. As you see, and let me return back to the MATLAB and let me show you the semi-log plot. Okay, so it was 32 iterations. Okay, for when lambda is 1. And this is how the error decreases. It's monotonic. And when you say that it's 1.2, so this is 1.2. Let me run it. Number of iterations decreases to 25. So there is approximately 20% decrease in the number of iterations. Let's try with the 1.4 once more. Now, as you see, it is just 21 iterations. So we are able to decrease the CPU time if our matrix is well conditioned. For the ill-conditioned problems, it is really it may be really problematic to use over relaxation, and it will certainly increase the CPU time instead of decreasing it. Over relaxation is basically helps to decrease the CPU time, where under relaxation helps us in improving the convergence. So that is the trait with the relaxation parameter. So do you prefer to converge, or do you want to calculate it in a faster manner? If you are sure that your matrix is well conditioned, and then you can use over relaxation. But certainly you have to find an optimum value, and there is no rule in finding an optimum value of the relaxation parameter. You have to continue with trial and error for your problem. In general, in many physical problems, once you set the parameter, you continue with it. So you do not continuously update the parameter. Okay, now just let's say that I want to write this error to a file. Now, let me say that output file. You can give a different name. Now, I'm just defining a variable. Oops, I have keyboard. Okay. And let's say that this is error output txt. I will generate a text file where I will write the numbers. Then I say that save. Now, next thing is to write the output file. Now, next step is what I want to write into this file. I want to write error vector here. How I want to write it? ASCII file command. Now let me run it. It gives an error. It shouldn't give me an error there. Ah, well, okay. I want to write it in commas. Yes. Now it's okay. Now let me open error output text file. You see my values are there. Certainly, you can read this file from another file, and in fact, you can load it with the load command. So let's do it like this. Now I write it load output file, and I say that error from file, and let's see whether it will get it. You see, these are the error values from a file. Now, error from file becomes my vector, and it just writes the values that gets from the output file into the error from file vector. Okay, so this is the thing about the Gauss-Seidel and Gauss-Jacobi method. Perhaps there are other iterative techniques like conjugate gradient, gradient minimal residual, and so forth. There are variants of the Gauss-Seidel method. One is the least squares Gauss-Seidel method. You basically multiply the coefficient matrix and all the right-hand side with transpose of the matrix. Then you will have a better convergence, and the number of iterations decreases significantly. Okay, so